This is your online module describing probabilities. At the end of this module, you will be able to identify different distributions of a random variable, calculate probabilities using common discrete probability distributions, and calculate probabilities using common continuous probability distributions. This is a summary of the last diagram that we had at the end of the previous online module. As you might remember, there are certain relationships in between the different types of random variables. For example, the log normal relates to normal, as well as the normal with the standard normal, and the chi-square and the f, respectively. So the color path here reflects those with discrete distributions in black boxes, while those continuous distributions that we will use in this course are in boxes filled black. So we're gonna cover a bit of each of these ones in this online module. We're going to talk about the specific examples and particularities about them, as well as how to interpret these distributions for the purpose of the future inferences that we're going to make. So let's start with discrete distributions. The first of them, geometric distributions, basically it talks about how much do you need to wait until you have a success in a Bernoulli process. So the requirements for this type of distribution is that the observation needs to be independent, they don't affect each other, and that they have the same probability of success at each trial, which means like they have identical probabilities. So the way that we represent it, of course, a probability of success is always represented by P, as well as its complement, 1 minus P, represents the probability of failure, as well as N representing the number of independent trials that take place. So in the general sense, the probability of success on the nth trial only is represented by 1 minus P, all to the n minus 1, and then P multiplied by times P, because that is the success that the only success that you're interested on. Like the first success, only one success, it's in your interest. So from there we know that also this distribution has certain characteristics, like if I know P, then I can estimate a general mean and a standard deviation in this way. So let's see an example for this distribution. So let's say that you are rolling a dice and you want to calculate the probability of rolling it 6 times in order to get the 6 in exactly the 6th roll. So that is the only success that we care about. So basically we define success here will be rolling the 6th, and then no success or failure will be defined as not rolling a 6, which is of course 5 other cases in the dice. Based on that, then we can multiply those probabilities. You know, the first 5 cases have don't have a 6, and then the last one does. So we reduce that expression to this, and the probability is 0.067. If we want to calculate the general mean of this distribution and the standard deviation, we have that it will take in average 6 rolls in order to get success with a standard deviation of 5.47 throws. If we want to calculate this through R, then we use this command, which, as you see, it can give you the exact same estimation like here. But in this case, it's important to notice that the first number actually represents the number of failures that you have before. So, for example, in this case, we are representing that we have 5 failures before the actual success, and the probability of the success was 1/6. Moving forward and talking about a binomial random variable, which is basically a Bernoulli experiment that's conducted n times. And in this case, in this type of variable, what we are interested on having is a set number of successes. So let's say in this case, in this example, we have that we randomly select 4 individuals to invite them to participate in an experiment. You are offering a monetary incentive, therefore the probability for them to accept is higher than random, and random chance for accepting or not will be like 0.5, right? And from previous experiences, you have estimated that that chance of people to accept, given the monetary incentive you are giving, is 0.65. So what will be the probability that exactly one of these persons will refuse to participate? Okay, so let's call these people with names in order to identify their patterns, right? So we have Alan, Brittany, Caroline, and Damien. So if we have that specific people for each circumstance, then we can have different scenarios. So we can have Brittany, we can have Alan refusing, or we can have Brittany refusing, we can have Caroline refusing, or Damien refusing. So it's 4 different scenarios. It matters which one of them actually is the one refusing. Therefore, because it's 4 possible scenarios, I do need to sum up all of those probabilities in order to get the final probability for one to refuse. So I will calculate it as 0.38, and the R command to get this done would be dbinom, which is basically you give the number of the number of failures. In this case, failure is the phenomenon of interest over the number of trials and the probability of that event, and then the numbers come up the same. So as you saw, what we are trying here is to find the number of successes k in a given number of trials n. So in this in the previous case k was 1, n was 4, and the probability was calculated based on the number of scenarios times the probability of each scenario. But when you have many scenarios, then it will become really tiring and time consuming. So we need to find better ways to calculate those, and I will jump into that into a minute. So but the probability of a single scenario is always calculated by p to the k times 1 minus p to the n minus k. So from there, let's jump into how do we calculate the scenarios. So for that, we use the choose function, and I know many of you may have never heard about this function, which is basically calculating the number of possibilities of choosing k elements from n possible elements. So in this case, this function is basically described as n factorial over k factorial times n minus k factorial, which mathematically represents, if you have never seen a factorial before, well, a factorial actually multiplies all the numbers up to that determined. Like in this case, for a factorial is 4 times 3 times 2 times 1, and so on. So once you do the math, then for k1 and n4 we have 4, for k2 and 9n we have 36, and this of course just keeps increasing. This is known as the this is known as the binomial coefficient, and in R you can get it as the function choose. So let's see another example of the binomial distribution. So in 2012 Gallup survey suggests that 26.2% of Americans are obese. Then if we get a random sample of 100 Americans, how many would you expect to be obese? So this is really straightforward at some point. Like, well, we just multiply the number of people that we have by the probability that these people will be obese, right? But there's also the knowledge that we have that the mean of the binomial distribution is n times p, and the standard error deviation is square root of n times p times 1 minus p. So we can use that as a more formally procedure. And then, of course, we wouldn't expect that always 26.2 people will show up from that 100, right? There will be always some room for error. And in that case, of course, we need to calculate the standard deviation. And we would expect that, yes, around 26.2 people will be obese, but with a standard deviation of 4.4. Remember that even though we are talking about successes and failures, in this case, we have averages and standard deviations that have decimals because we're talking about the long-term performance of it. So it's totally valid that we have decimals here. So from there, let's recall that if we have things that are beyond 2 standard deviations from the mean, then we consider them unusual. Not necessarily outliers, but unusual. So because most of the data is centered around those 2 standard deviations. So let's say that in order to see if what we saw is something that we see is really weird to see, then we find that range for the mean, the expected mean, right, plus minus 2 times that the standard deviation. And then we find this range of 17.4 and 35.0. So if, for example, I get a sample of Americans that has 10 people that are obese, then that sample will be unusual because it will be beyond the lower level of my regular range. So let's get another practice problem in terms of another survey suggests that 13% of Americans think homeschooling provides an excellent education for children. So the question is, with a random sample of 1,000 Americans where only 100 share this opinion, be considered unusual. So let's see. If we do our numbers and we get the expected value, it would be 0.13 times 1,000, which is 130. That will be our expected mean. And then we calculate our standard deviation, which is 10.6. If we do the regular range calculation, then yes, 100 Americans having this opinion is actually below what I would have expected from calculating that range. The other thing that I could do is to actually use the z-score, because we know that the binomial distribution converges to the normal. So we can use the z-score by using the target value 100 minus the mean over the standard deviation, and then we will get that it's actually 2.83 or almost 3 standard deviation below the mean. So it's definitely considered unusual. So remember that in order for the binomial distribution to approximate the normal, we need a large n. And by large n, what you need, the rule of thumb, is that n times p, which is the proportion that you have of the success of whatever thing you are analyzing, is greater or equal than 10. So as a consequence, of course, if you do also the calculation of n times 1 minus p, then it should also be greater or equal to 10. So for example, if we have 10 observations only and p of 0.13, this is 1.3, definitely not enough. And then if you do the opposite, it will be 8.7. So any of them, none of them actually reached the 10 threshold. Therefore, with this small data size, I wouldn't be comfortable with moving forward with a normal approximation. This is the case for the upper left corner in here, but then we will need to check how that performs with N30, N100, and N300. I am pretty sure that this one, as you see graphically, this will be totally okay to approximate to a normal. So finally, in terms of the binomial distribution, let's do a final example here. Let's say that a recent study found that Facebook users get more than they give. So the facts that they showed is that 40% of Facebook users in our sample made a friend request, but 63% received at least one request. and the user in our sample press the like button next to friends content an average of 14 times, but they had their content liked an average of 20 times, and users sent 9 personal messages but received 12. Finally, that 12% of users tagged a friend in a photo, but 35 were themselves tagged in a photo. This might be explained by some people having a lot of power in this type of interactions, right? Like there are people that actually are most fast posting or replying and things like those. So they came up with a definition of power users, and the fact that power users actually contribute much more content than the typical user. So for practice, let's see that this study also found that approximately 25% of Facebook users are considered power users. And the average Facebook user has 245 friends according to this study. So what will be the probability that the average Facebook student, a user with 245 friends, has 70 or more friends that could be considered power users? So here the success is defined as being a power user or not, which is p equals to 0.25, and the n that we are given is 245. So we need to check, of course, the assumption of independence, if that we could investigate if we would have access to Facebook data. So in theory, right, what I would do is, okay, what is the probability of x being greater or equal to 70, which is 70 or more friends that would be considered power users. So I would need to sum a probability of k equals 70, and then 71, 72, etc., all the way to 245. But this is definitely tiresome. So the shortcut would be to use the approximation to normal. So once you calculate your mean and your standard deviation, right? So you calculate mu, which will be 61.25, and your standard deviation, which will be 6.78. Then this binomial distribution that you had can transform into a normal with mu 61.25 and the standard deviation of 6.78. Okay, so as you see, these two distributions are overlapped here and they fit quite well. So from there, of course, we can use this distribution, this normal distribution, to calculate a z-score of the observed minus the mean over the standard deviation, and it will give me a standard a z-score of 1.29. What's the probability of the z-score being greater than 1.29? This is the equivalent of 1 minus 0.9015, which is less than 10%. So this calculation, we're going to go to a little bit more detail in the online module on the normal distribution. So don't worry about that too much, but if you have watched that, then this should have made complete sense for you already. And how do we calculate that in R? Well, this is this function p-norm, and I would perform this calculation to get the result. Finally, another discrete distribution. Let's imagine that a college student is working at the psychology lab and is asked to recruit 10 couples to participate in a study. So she decides to stand outside the student center and ask every fifth person leaving the building whether they are in a relationship, and if so, where they would like to participate in the study with their significant other. So of course, this is a Bernoulli process. They either accept, which is success, or not, which is failure. This person needs 10 successes. So let's suppose that the probability of finding such a person is 10%. What is the probability that she will need to ask 30 people before she hits her goal? So P is 0.10, but interestingly here, I am caring about the order of my successes, because it's saying I sample 30, but she will stop at 30. Therefore, in order to stop at 30, I need 29 successes before, and my final success to happen exactly at trial 30. So this will represent 10 successes in 30 trials, but with a 10 success happening at the 30th trial exactly. This is actually a negative binomial. which will be represented by this. As you can see, the combination of results will now be reduced by 1 because I have like 29 previous trials from which I got 9 successes already, and those I really don't care about the order, so give me whatever. And then I get all the successes I get, and then the failures that I got. But the final success needs to be at the end. Therefore, the last one, the location of the last success is not compromised. So the calculations accordingly will be this. It's really, really low. Again, this is a summary of the negative binomial. The conditions are basically the same, mostly, like the trials are independent. They are basically a Bernoulli experiment. They have the same success, probability of success for each trial. And in this case, in particular, the last trial must be a success. So here's a summary of the probability of this. So finally, the Poisson distribution is a random variable of an event that is considered rare, and the population is large, and the event occur also independently of each other. So here's what we know, that an airline occasionally will lose a bag. And let's suppose that a small airline has found it can be reasonably model the number of bags lost each weekday using a Poisson model with a mean of 2.2 bags. So this is how the probability of a Poisson model works with a parameter which is lambda, and k is the number of events that are observed. So what is the probability that the airline will lose no bags next Monday? That will be represented by k equals 0. So we substitute k equals 0 in this function, in this formula, and we find that it's around 11%. What is the probability that the airline will lose 0, 1, or 2 bags on next Monday? These are independent events. They are not independent. The lack of they are independent, I confirm, and then the fact that they are independent actually makes us sum up those events. So we need to sum up the probability of 0, probability of 1, probability of 2, which will give me a 0.62 probability. And finally, what is the probability that the airline will have at least 1 bag lost on next Monday? So when we talk about at least, then we need to consider our complement capabilities. So if we at least have 1, then instead of counting 1, 2, 3, 4, 5, 6, etc., till infinity, I better calculate 0 and remove it from 1. So that probability will be calculated through this calculation, and it's 0.88. So this is the way that these calculations will be made through R.